Me here. Terrific. Sam, please go ahead.
Thanks very much. Yeah, thank you very much for the invitation. It's really nice to speak at this seminar series. I'm one of the people that usually catches up with things on YouTube a couple of days later, often at sort of 1.5 speed because I quite like doing things that way. But I think it's a really nice initiative, and it's also really nice that all the talks are on YouTube, and because when I have sort of new students or something, I can point them to talks from like a year or two ago that I remember, and they can still watch them and catch up. I think it's really, really nice. So yeah, I want to talk about some work that two different projects together with my former PhD student Max Hurd, who's now a postdoctoral researcher at Waterloo in Canada. And they're both kind of connected around the same theme of preconditioning MCMC sampling algorithms. Okay. What is it not? Yes. Okay, good. So, right. So this slide is completely redundant for this audience. So let's go through it a little bit quickly. So, okay, various forms of statistical inference, including Bayes. We're constructing probability distributions that express kind of a priori, a posteriori beliefs about an unknown parameter or latent variable. So I'm just setting notation here. The target distribution that I'm talking about for this talk is going to be denoted pi, and the state variable is going to be denoted x. So if you're more of a kind of statistician, you might be thinking about theta usually as your state variable. I'm using more kind of conventional Markov chains literature notation of x. So if I want to extract information about this posterior distribution in the Bayesian context, I'll want to do some integration. And if I want to do integration, typically I'm going to end up doing some kind of Monte Carlo method if I can't do things exactly. The Monte Carlo method of choice, when the dimension of x is large, and I have certain conditions which are usually satisfied for Bayesian statistics, like I only know pi up to some normalizing constant. Then the sampling algorithm of choice is typically Markov chain Monte Carlo. It's certainly not the only thing you can do. There's lots of exciting alternatives out there, but I think it's still probably the first thing you would think of for many problems. And this is about constructing a Markov chain with a user-specified limiting distribution pi and then simulating a realization of the chain. And typically we want to construct faster mixing Markov chains and get ergodic averages that have smaller variance, right? And this is really with the end goal of having more accurate computation of integrals with respect to this distribution of interest. So all of this is to say something which this crowd certainly already knows, which is that effective statistical inference in this context means effective sampling algorithms, which in the MCMC setting means designing Markov chains that mix quickly to their limiting distribution, right? And so this is kind of the motivation for the talk, right? So the Metropolis-Hastings algorithm is, of course, an extremely well-known example of such a procedure for constructing a Markov chain with a user-specified limiting distribution. And the key design parameter in this guy, and I've got an example on just a d-dimensional Euclidean space where the target and proposal both have kind of densities with respect to Lebesgue measure. The key design parameter is this proposal transition kernel, right? Metropolis-Hastings is kind of like a meta algorithm or a family of algorithms. The performance of the algorithm is really driven by what choice you make here, you know, and how that kind of interacts with what the target distribution is. So there's various generic choices, you know, and two obvious ones are random walk Metropolis, where my proposal is going to be generated by looking at the current state and adding some symmetric zero mean noise to that. So here's an example where the noise is Gaussian, right? And if you do that, then the acceptance rate kind of reduces to this kind of much more sort of friendly form. But you can do more advanced things. So, you know, the Metropolis adjusted Langevin algorithm is a good example where you take the sort of current state xi, and then you sort of perturb the mean of your proposal distribution in the direction of a local mode of your target, right? So it's kind of using information about pi in order to hopefully design slightly more informed proposals. And both of these algorithms are things that have been discussed many times in this seminar series, and I think most of the audience are familiar with them. But the point is they're sort of generic recipes that hopefully for a wide class of target distributions will produce a sensible Metropolis-Hastings algorithm, right? Okay. So what is preconditioning, and how does this come into the story? So preconditioning in the abstract, and it's not something that is unique to sampling algorithms by any means, but in the context of sampling algorithms, what are you doing with preconditioning? Well, you apply some kind of transformation to your state variable. So I'm going to produce a new state variable y, which is going to be a transformation of my original state variable x. And if x follows distribution pi, then that induces a kind of distribution for y, which I'm going to denote by pi tilde, right? And then I'm going to run my MCMC algorithm on this different space, i.e. targeting this different distribution pi tilde, right? And after I've run my MCMC sampling algorithm, I can then transform my samples back to my original space and generate samples from a Markov chain which will converge to my original limiting distribution pi, right? So why is this a thing? Because most MCMC algorithms that we use, not all of them, but many of them, are not going to be invariant to this kind of transformation, right? And so depending on what you do, how you transform your variable, you may end up in a situation where your sampling algorithm is going to mix more quickly, right? So that's essentially the goal, right? Can we design a transformation here which will make this middle stage produce a very fast mixing Markov chain, right? Okay, so let's solidify things with a concrete example. So this is an example where the transformation is linear and the algorithm is the random walk metropolis. So we'll just consider a really simple multivariate Gaussian target distribution with covariance matrix A to the -1. Now, here I've got quite a lot of information to design a sensible linear transformation here. So I'm going to map the state variable x into a new state y through the transformation a to the half x, so whatever your favorite matrix square root is. And this will induce a new target, which is just a standard Gaussian in this case. Right. So then I'm going to run the vanilla algorithm on this kind of transform space, right? So I'm doing a vanilla random walk metropolis on the y space, right? So my current state is going to be ya. My proposed I'm going to denote by y prime, and I'm going to accept or reject the state based on pi tilde. Right? So let's think a little bit more carefully about what we're doing here. Okay, so given yi is my current state, I can sort of map that to a kind of xi, which is going to be, some linear transformation of the yi, and think of, well, that's the kind of equivalent current state on my original space. And then I can write my proposal in terms of that original xi here. And then I can go one step further and say, well, let's imagine that this proposal y prime is also something that can be written a to the half times some x prime, which is kind of a proposal on the original space. And then if I multiply everything through by a to the minus a half, I can see that I've kind of induced an algorithm on my x space, right? And it's slightly different to the algorithm on my y space because it's a random walk metropolis, but with this covariance of my proposal being a to the -1 rather than the identity. And because in this case, the transformation is linear and the kind of Jacobian doesn't depend on the current state, then the acceptance rate of this induced algorithm on the original space is just the ratio of the original pi's. So this kind of induced algorithm on the original space is often referred to as the preconditioned random walk metropolis, right? And the limiting distribution of this induced algorithm is pi, the original distribution that we targeted. So if people have sort of learned about preconditioned algorithms in the past, you probably will have learned about the kind of induced algorithm. That's what I learned about when I first studied MCMC. And there are kind of equivalent sort of preconditioned versions of other popular algorithms like Mala that we saw on the previous slide, and also Hamiltonian Monte Carlo. And in the case of Hamiltonian Monte Carlo, this corresponds to choosing a non-identity mass matrix for your algorithm. This is the kind of preconditioned version of the algorithm, right? And so this is very popular in all the kind of standard software. But the point I'm trying to make in this slide is that the applying the vanilla algorithm on the transformed space, which is this yi chain here, or running the kind of preconditioned algorithm on the original space, which is what I've denoted by this xi chain here. Somehow these Markov chains are very similar to each other. They're what's called isomorphic Markov chains. You can map between them with a deterministic transformation. And this kind of means they share lots of different mixing properties. In particular, they have the same spectral gap. So the point is really, if you want to understand preconditioning, you can sort of study either of these two things, right? You can study the Y chain, and then you're working with a simpler vanilla algorithm, or you can study, and this is effectively you're changing the target distribution, or you can study the induced preconditioned algorithm where you're keeping the target distribution the same, but you're changing the algorithm, right? And depending on what your needs are, will sort of determine, what the best one is to do. Okay, so the matrix kind of a to the half here that I've used to transform between the space, we'll call that the linear preconditioner. And in the context of linear preconditioning, there are some sort of generic recipes for choosing what we think heuristically are good linear preconditioners for a particular target distribution. Of course, in the Gaussian case, it was kind of easy. We had this covariance, and we knew we could apply that matrix and create something which is standard Gaussian, and it's fairly believable that that probably is something that will be easy to sample from. But in a generic setting where we have a generic pi and we don't necessarily know much about it, we have some kind of guideline recipes, right? So one of them is to sort of estimate the covariance of the target distribution using either some pilot runs or within a kind of adaptive MCMC algorithm, and then use that. And that's what's typically known as dense preconditioning in STAN, for example. You can just focus on estimating the marginal variances. And this is what's known as diagonal preconditioning in the same software. And for obvious reasons, that's computationally cheaper because you're manipulating a diagonal matrix. Or you can do certain other things that make quite a lot of sense in particular contexts. So one that is often kind of done heuristically is to run an optimizer to find the mode of the target distribution and then use the Hessian at the mode in some way, right? And steps 1 and 3 are going to correspond to using a to the half in the Gaussian case. And so you can see where these kind of choices came from, that you can see in the Gaussian case, they make a lot of sense. And I guess we're sort of hoping that beyond the Gaussian case, they also do. And this is really the sort of questions that we started asking in this study, to what extent is that true? Right. Okay, good. So just pictorially to kind of emphasize what I mean here. So this is an example target distribution on the left with kind of different scales. The first component has a much larger scale than the second. And if we're using a vanilla random walk metropolis, if the current state is in the middle of this kind of dartboard here, and this kind of represents the proposal contours, you can see that we might get unlucky because quite a lot of kind of the mass of the proposal might send the proposal to regions that are very unlikely under the target distribution, like these kind of edges here and here. If we apply the transformation to make the target distribution more isotropic, then intuitively it feels like the kind of proposal is going to land us a bit more safely in kind of regions that are more sensible. And so this is applying the vanilla algorithm on the more kind of regularized isotropic kind of target distribution. And then if we map and look what that's doing on the original space, where we've got the original target distribution, we've effectively changed the proposal to sort of make the scales of the proposal match the scales of the target. And again, here now we see that we're much less likely to make these moves that will send us to very low probability regions. So the message of this slide is these two algorithms intuitively feel like they might do a better job of sampling than this one, right? And this is what we want to try and sort of discuss more precisely, right? Okay. So why am I interested in this? Well, I think my own personal experience is that empirically speaking, preconditioning is one of the things that can improve the quality of your sampling by the most. It really is a very effective practical technique in a lot of settings. Not always, but in a lot of settings. It's one of the first techniques I learned as a student myself that I saw really made a difference. It's something that I always teach in my own courses, and it's also something when I'm kind of reviewing papers and there's new methodology and someone's comparing to an existing algorithm, it's one of the first things I'll check. Well, did you precondition the existing algorithm? Are you really comparing with like the best thing you could compare? Because I know that it can make things a lot better. Here's a sort of simple example of this in a much overused kind of Pima Indian dataset logistic regression scenario. So the left-hand side are trace plots without doing any preconditioning, and the right-hand side are trace plots for the same coordinates after preconditioning. And you can see just heuristically that things look better here, right? So the first kind of project and the main thing I want to talk about, the first thing that Max and I really thought deeply about during his PhD was to try and say something precise about when and by how much this technique actually improves the quality of MCMC sampling algorithms. Okay. So if we want to say something precise, we're going to need to work with a class of models for which things are known reasonably precisely. And I think up until about a decade ago, this would have been extremely difficult to do because most of the kind of results on MCMC theory were quite qualitative in spirit. They're sort of commenting on the existence of a spectral gap or whether or not an algorithm produced a geometrically ergodic Markov chain, but saying something precise about the quality of the mixing time, it was known that a lot of bounds were very loose. And I think to some extent this changed over the last 10 years with the introduction of certain sets of assumptions under which quite more precise bounds could be established. And this is the kind of class of models which I'm going to call well-conditioned distributions, which I think has already been spoken about a few times in this seminar. So let's mention it. So let's assume that our target distribution is on a Euclidean space and has a density, which I'll write e to the minus u, and I'll call u a potential. And the kind of assumptions that have been made under which interesting mixing time upper bounds have been established look a little bit like this. So if we imagine the potential is twice continuously differentiable, for example, then you're imposing kind of upper and lower bounds on the eigenvalues of the Hessian matrix, right? So this left-hand side bound here is what's typically referred to as the potential being little m strongly convex. And the right-hand side here is kind of referred to as big M smooth. You can also think of it as U being gradient Lipschitz, right, with Lipschitz constant M. And if you have both of these bounds, then we will call the target distribution pi well-conditioned. And we've taken this from the literature. We're not the first people to use this term. So if you have such a target distribution with this kind of control on the Hessian or equivalent control in the case where you're not C2, then you can define this notion called the condition number, right, which will denote kappa, and this is the ratio of big M to little m, right? So it's always kind of trivially guaranteed to be at least 1. But the kind of idea, which I'll show to be true in the next slide or two, is that somehow you want this condition number to be smaller, right? The idea is somehow a smaller condition number is connected to a better sampling algorithm. And you can see this through a kind of plethora of existing results that I'll show on this slide here. This slide was actually made by Max, which is why it's got this kind of stylish background. So if you look on the left-hand side, we've got kind of some spectral gap results, and these are just a snapshot of the literature. It is a very fast-moving literature where, lots of kind of bounds are appearing all the time, which kind of trump existing bounds. And so I'm sure a lot of this stuff is out of date already. But the spectral gap results on the left-hand side, a bigger spectral gap is better for a sampling algorithm, right? And in all of these bounds that we have here, we've got this condition number kappa on the denominator of these kind of results, right? So this tells you that a larger condition number is going to result in a smaller spectral gap, right? Roughly speaking, right? On the right-hand side, we've got the kind of epsilon mixing time. So this is something where we want this to be as small as possible. And now we've got this kappa condition number as a multiplier, right? Either kappa or some power of kappa as a multiplier. So again, we want the smallest possible condition number here to make the smallest possible upper or lower bound on the mixing time, right? Okay, cool. But let's dig into this quantity a little bit more and try and understand what it's really measuring. So this kind of condition number, it's really capturing two things for a general target distribution. And this is something that took us a while to really think about and digest. And it's kind of crucial to understanding how well preconditioning can help the sampling. So it's really capturing kind of at a single state X, how much heterogeneity there is in the Hessian matrix between different coordinates, different dimensions. But it's also kind of combining that together with how this Hessian matrix changes throughout the state space, right? So you can define this condition number, write it slightly differently, like this, and then you can sort of relate a little bit more to sort of notions of condition number in like numerical linear algebra, for example, where you have a fixed matrix A, but if you remove the kind of suprema, then you'll have this kind of definition of condition number for a typical matrix. So you can sort of see how this kind of object relates to that and why it's been given a similar name. So if we look at the Gaussian case, for example, then the Hessian, this is the kind of the setting where the Hessian does not depend on the current state, right? And so then it's not very hard to see that the condition number ends up being the ratio of the largest to the smallest eigenvalue of the covariance matrix. So this is a sort of unique setting where there is no kind of supremum operation happening here, right? It's just purely like measuring kind of at any particular state, how much heterogeneity is there within the Hessian matrix at that state? How much do the eigenvalues differ? But you can construct different target distributions where almost the opposite story is true, right? So here's an example of a Hessian, just a one-dimensional target distribution. And we've written it as a function of some sigmoid function, which goes from 0 to 1, right? And so basically, as x goes to minus infinity, this Hessian is going to be 1. And as x goes to plus infinity, this Hessian is going to be omega, right? And omega is arbitrary here, right? So I can make omega as large as possible, and the condition number is given by omega. So I can construct a target distribution with an arbitrarily large condition number here, which is kind of nothing to do with heterogeneity between different dimensions, right? So you can see that this thing can be large or small for quite different reasons, or at least it can be large for quite different reasons, right? And this is kind of helps us a lot with our kind of thinking and study. So how does preconditioning play into this story and how we're going to study it a bit more precisely? Well, if you apply a preconditioner, you'll get a new target distribution pi tilde, and this will have a new potential u tilde, right? And so then we're going to have a different condition number, kappa tilde, right? Which is based on the Hessian of u tilde now. And so we're going to seek conditions under which one can apply a preconditioner such that kappa tilde will be small, right? And then we can relate this to kind of different improvements, levels of improvement or lack of improvement in the quality of our sampling through spectral gaps and mixing times. So we're going to focus in this study primarily on linear preconditioning. So just the case of a linear transformation. And this is really because this is by far the dominant thing that is used in practice and in the kind of all the major software packages. So there are nonlinear preconditioners that exist. There are papers about these kind of things. I would say they're in a much more early stage of their development. And of course, as soon as you move away from linear preconditioning, you're in a complete sort of open field of what to do. We've thought a little bit about this, but we decided to sort of focus on the linear case initially, at least. So just to kind of hammer home before I give some results, like what we're really thinking about here, a more kind of realistic plot of what a target distribution might look like is on the screen in front. This is from a logistic regression setting. And on the left-hand side, the red plot here is a sort of two-dimensional contour of what a kind of logistic regression target distribution looks like before applying a linear preconditioner. The same target distribution after preconditioning in an appropriate way is the green one on the right-hand side. And so it might be tempting to sort of assume that maybe the green target distribution is easier to explore than the red one. But it's far from kind of concrete that we can really conclude this. We've still got quite a lot of skew in the distribution. There's some sort of interesting shapes happening here. It's not really clear that this is a better thing to sample from than the red guy, right? Maybe it feels like it is, but it's not 100% clear. It's not like the Gaussian case where you're mapping to a standard Gaussian. So we want to sort of say, to what extent is this thing a better thing to sample from, Okay. So what I'm going to do is present the kind of 5 key headline results for the paper in much more kind of main results section. The first one is actually a negative result. So the first one is saying that being well conditioned is not enough to guarantee that a linear preconditioner will improve the quality of sampling. So the precise statement is that for any choice of kappa and any dimension d, there are distributions on d-dimensional Euclidean space that are well conditioned with that condition number kappa, such that no non-orthogonal linear preconditioner can in any way make the condition number the same or lower than what it already is. So in other words, linear preconditioning cannot reduce the condition number, and anything that is non-orthogonal as a linear preconditioner will actually make the sampler worse. So what's the message of this result? It's basically about the class of well-conditioned distributions, which is the class for which I feel comfortable saying something precise in this context. Okay, we can relax it slightly and things, and I'll talk about that at the end. But the class that I'm sticking to, which I know I have some reasonable mixing time bounds, that class does not intersect perfectly with the class of distributions for which I can apply a linear preconditioner and expect things to behave better. There are suitably strange looking distributions in that class that I can't linear precondition well. This technique won't help. Right? So here's a kind of really simple example of one, right? So this is a two-dimensional target distribution where as the x1 coordinate shifts to minus infinity, the Hessian looks a lot like 1, 0, 0, 100. And if I go in the other direction, it looks a lot like 100, 0, 0, 1, right? So you get this kind of strange egg-shaped distribution, right? Now, this is not a distribution that's really difficult to sample from, right? It's still reasonably isotropic. Much of the center of the space looks fairly kind of isotropic, symmetric, spherical. But it is one for which I cannot precondition and reduce the condition number. So this is the kind of distribution that I'm thinking of. All the kind of contours create convex sets. It's clearly got some curvature. It's clearly within the class, but it's not one that's going to play well with linear preconditioning. So if I want to say something positive, I'm going to have to impose more assumptions, right? So this is what we did next. So we imposed a few different types of assumptions and saw what we could say. So one set of assumptions we broadly characterize as kind of additive structure, right? So we kind of suppose that the Hessian can be written as some kind of matrix A, which does not depend on the current state, plus some matrix B, which does, but such that the matrix B is kind of controlled in its size, right? So that the most kind of loose assumption that we made, the weakest set of assumptions that we made is just to control the kind of the norm of this matrix. But then we sort of went a little bit more restrictive and we said, okay, well, let's put precise bounds on all the kind of eigenvalues and eigenvectors of the Hessian and how much they're allowed to change, right? And then we weaken that slightly to using some kind of matrix perturbation theory, results like the Davis-Kahan theorem and Wiles inequality to relate that to sort of properties of the norm of the Hessian. And then our final weakest assumption was really just to sort of assume this thing here, right? And the weaker the assumptions, the weaker the bounds we get. And in the kind of most restrictive case, we get very sharp, very tight control over what's going to happen to the condition number. But all of our bounds look something like this. So it says if you have this kind of structure such that you can control effectively the amount the Hessian is changing, then there exist these kind of valid linear preconditioners, meaning a choice of linear preconditioner for which the resulting target distribution has a kappa tilde that is smaller than or equal to 1 plus some function of whatever this epsilon is, right? And this, yeah, obviously the hope is that this H epsilon is small. So we have an explicit expression for what this is. It kind of grows monotonically with epsilon, and as epsilon goes to 0, this does too, right? So what do I mean by a valid preconditioner? A valid preconditioner, I mean, in the case if I've got the Hessian having this structure here, I can choose a to the half. But in terms of the kind of generic recipes that people use in praxis, well, under sort of slight additional assumptions, the covariance is a reasonable choice. This kind of Fisher matrix, which was proposed recently by Mihalis Tsitsias, is also a pretty good choice, right? So we examined a few of the kind of standard choices and validated that they fall within the class. Good. Okay. So it's quite a restrictive set of assumptions, but what it's really doing is kind of measuring how far away from Gaussian is the target distribution and at what rate does that kind of technique, which works really well in the Gaussian case, degrade, right? Because we know this approach in the Gaussian case will reduce the condition number to 1, right? So as we move away from the Gaussian case, as measured by this part of the Hessian that's allowed to change, we're trying to capture at what rate this kind of condition number reduction degrades, right? Okay. So here's a kind of very sort of simple example, which really just says linear preconditioning works. So I don't want to labor on this too much. The next kind of result is a slightly different structure because we observed that in lots of kind of, for example, generalized linear models, the Hessian has a kind of structure that's a little bit more like this, right? And we call this kind of multiplicative. So here you can imagine the matrix Z to be some kind of design matrix, right? So Z kind of represents data, right? So X is my state, so my kind of parameter. And so I'm using Z for my data here. And this kind of structure here is very common in a Hessian matrix where you have, for example, a generalized linear model with like a Gaussian prior, right? So yeah, and so this is a kind of known structure where certain strategies are applied as a sort of standard to kind of precondition algorithms, not just sampling algorithms, algorithms in general. So here, some standard sort of things that are tried are to take the kind of design matrix, apply a QR decomposition, and then precondition with the matrix R effectively. So this is what's kind of typically known as kind of orthogonalizing the data or like standardizing the data before doing your analysis. And you can sort of show that this is a good idea effectively, because if you do this, then after that, your condition number after the transformation ends up depending wholly on this matrix lambda in the middle. Whereas if you don't do the preconditioning, you're essentially multiplying this guy by the condition number of Z transpose Z, right? And that thing is guaranteed to be bigger than or equal to 1. So this is guaranteed to be smaller or equal to the original thing you have. And then you can sort of apply this on the same kind of conditions we had on lambda. We can assume some sort of additive structure to it like we did in the previous result and make more concrete statements. We considered a slightly different preconditioner here because we could see that it might have some advantages, and that's this kind of Hessian at the mode strategy. And if you do that, you can then establish a bound that is slightly different because you're effectively then measuring the eigenvalues of this product of lambda evaluated at the mode inverse multiplied by lambda. So we observed that this condition number here might be smaller than in this first case if you're in an instance where this lambda matrix has quite a lot of heterogeneity, but that it doesn't change much with X, right? And so we found that this would be something that happens, for example, in a binomial regression, where you have different kind of sizes for each observation. So if each observation is the number of successes from M trials and M varies with the observations, but it can be quite large, then this kind of strategy might do better than this one. And this is what we found empirically too. Good. Okay. Okay. So here's another example which basically says preconditioning works. So again, I don't want to labor this, but I would check it out in the paper if you're interested. So the kind of what we've done so far is to say that if you do linear preconditioning under the right assumptions, under the right conditions, you will reduce this condition number, right? And from our previous look at the literature, what we can then conclude is that mixing time upper bounds will be smaller, right? And spectral gap bounds will be bigger, right? But that's not necessarily guaranteeing that there's a concrete improvement in the sampling, right? Because it could be that those upper bounds are just quite loose. And so just because we've made the upper bound smaller doesn't necessarily guarantee that the actual mixing time is better, right? So we wanted to say something slightly more precise, and we were able to do that for the random walk metropolis. So let's work with the same kind of additive Hessian structure assumption that we had in result 2. If we have this kind of assumption, then we have the following kind of upper and lower bounds on the spectral gap of the random walk metropolis. And the lower bound here is taken directly from the literature, actually some of the work from Sam and his co-authors, Christoph, Andrea, Anthony Lee, and Andy Wang. The upper bound is a modification of their result. And the point of this result is that we have the same dependence on the condition number in both the upper and lower bound, right? So this tells us that the spectral gap is exactly of this order in kappa. So how do we go about establishing this? Well, like I said, the left-hand side is directly from the literature here. What we did in the upper bound, well, the spectral gap can be defined as an infimum over a Dirichlet form evaluated over a class of functions, unit variance functions. And so if you pick any function and just evaluate the Dirichlet form for that function, you get an upper bound, right, for what this thing is. And so in this work, the authors chose a linear function for the obvious reasons that they can compute things. And what we basically did was, under this kind of additional assumption that we have here, where we knew something about the kind of the spectral structure of the Hessian, we were able to be careful about what kind of linear function we chose, such that to kind of engineer an upper bound which gave us the right kind of condition number dependence. So they weren't able to do this because they weren't making this additional assumption. You can't do this in general, but because we'd imposed this, we can then engineer the function and get a slightly better upper bound. And there's a nice kind of corollary of this, which enables us to say what we wanted to say, which is that if the preconditioner that we choose satisfy the results, the assumptions required in the second result, and the condition number to begin with of the original problem is sufficiently large, then applying this linear preconditioner is guaranteed to increase the spectral gap of the random walk metropolis. And the kind of proof approach of that, it's pretty simple, really. You look at the spectral gap after preconditioning. You take the lower bound on this, which is going to depend on the kappa tilde that you got after preconditioning. And you basically want conditions under which this lower bound is bigger than the upper bound before preconditioning, which depends on this blue kappa here, right? And that's an upper bound for the actual spectral gap before preconditioning. So provided that you have this kind of relation between kappa and kappa tilde, you're going to be fine. And under the second result, we know that we can make kappa tilde quite small. So then you just have an absolute, the original condition number has to be sufficiently large, and then you have your result. So that was good. That was something concrete that we were able to say, and we were very pleased with that. But we have one final result for the paper, and this is actually a negative result again. And this was, in some sense, the most kind of surprising result that we found. And this is looking at diagonal preconditioning. So the statement of the result is precisely that there exist well-conditioned target distributions for which the sort of natural diagonal preconditioner, which is just looking at the marginal variances and kind of standardizing them all to one, will result in a condition number which is larger than the original. But if you applied a dense preconditioner, you would be able to reduce the condition number to very close to or exactly one. Right? So this is slightly different to the first result, which was saying that there are target distributions for which no linear preconditioner will be able to improve things. This is saying that there are settings for which a linear preconditioner will do really well, but the standard diagonal preconditioning strategy is a really bad idea, right? So this surprised us a lot because diagonal preconditioning is often the default in a lot of the software that is used, and it's for a good reason that it's much cheaper to apply. It's a diagonal matrix, so it's a linear in dimension cost. And the general assumption is that, well, you can't do any harm, right? It's kind of better than nothing. You probably achieve something, and in the worst case scenario, you won't achieve much. So it surprised us to see that there are real examples for which it can do a lot worse than nothing. And here's a kind of simple example illustrating exactly that. So this is a Gaussian target, a five-dimensional target distribution. And on the y-axis is the log of the effective sample size. So a bigger value is better here. The red boxes are dense preconditioning. You can see that the ESSs are doing pretty well here in all the dimensions, pretty homogeneous. The blue boxes are no preconditioning, and the green is diagonal. And you can see that in dimensions 2, 4, and 5, the effective sample size is clearly higher for no preconditioning than diagonal. So in the Gaussian case, the problem basically boils down to find me a covariance matrix for my Gaussian for which the correlation matrix is more ill-conditioned, right? So that's what diagonal preconditioning will do for you, or map the target distribution from using its covariance matrix to using its correlation matrix in this context. The most common question I get asked when I present this result or when Max presents this result is, and this is what we asked ourselves as well when we first did it, is how common is this? Is this just some weird kind of quirky example that we're never really going to see in applications, or is this something we actually need to worry about? And the only answers I can give to this question are, well, we generated this example by rejection sampling. We just generated matrices from a Wishart distribution and then stopped when we found one with a higher correlation matrix condition number. And the rejection sampler converged really fast. Like it wasn't a hardship for us at all. And then shortly after we kind of archived this, within the next year or so, we were contacted by some kind of, some people that we know in Canada, and they mentioned that they were working on a kind of methodological project where they'd exactly found this phenomenon, where like they were testing out some samplers on a real kind of target distribution, and they'd found a strange setting where the diagonal preconditioning was doing worse than no preconditioning. And initially they thought there was kind of a mistake in their code, but then they sort of came across our paper and realized this is what's happening. So I can only sort of comment on that like there does exist a real example, at least once, that people have been trying to fit this on. And when we tried to construct one out of toy examples, it wasn't difficult. Okay. So that's the first project, and that's by far the bulk of the talk. I did just want to give a couple of slides at the end on what Max has been working on since, which is kind of a follow-on piece of work, a little bit more methodological. And this is on designing kind of novel linear preconditioners, motivated largely by result 5 of the previous work. So we have seen that diagonal preconditioning can be problematic. There are examples for which diagonal preconditioning does badly when a dense approach will work well. So why not just apply dense preconditioning? Well, the problem is that even in the most efficient way of applying a dense preconditioner with no kind of additional structure to the matrix, it's going to be a quadratic cost with dimension. And if you do things naively, it's going to be cubic, right? Doing things with a diagonal matrix is just linear, and that's a big saving, So this begs the question, can we somehow capture the key correlations of the target distribution and design a good linear preconditioner, but still keep with a kind of sub-quadratic cost so that, we're saving something compared to the dense case? Okay, so this is what we started asking ourselves. So when you start posing this question, it's quite natural to consider kind of diagonal plus low rank type structure for your matrix. And we did explore this option ourselves. From our own experiments and investigations, we found it difficult to sort of learn such a preconditioner adaptively using kind of MCMC output in the natural way that you would. Perhaps others can figure that problem out for us, but when we kind of experimented in what we thought were kind of the natural ways, we couldn't really get it working very well. You can take such a kind of diagonal plus low rank matrix and take a kind of VI pre-training strategy where you learn a Gaussian approximation to the target with the diagonal plus low rank covariance, and then you kind of use that as a preconditioner for your algorithm. And we did that and tested it out compared to our approach, because some friends that have recently kind of worked on this in the variational inference context. But one thing that you can do reasonably well adaptively during an MCMC sampler is learn the top few eigenvectors and eigenvalues. There are various kind of algorithms that exist in the kind of incremental PCA literature for doing this. One example is Oya's algorithm, which is on the screen now. Another example is CCI-PCA, which has previously been used quite well in sort of generalized Hamiltonian Monte Carlo for estimating the top eigenvector. And we found that these things can be learned quite efficiently. So if we're looking at this equation here, I'm basically incrementally learning the top m eigenvectors using just the current state of my Markov chain and some running estimate for the mean and some kind of learning rate eta here, right? So the cost of doing this kind of learning is dm squared. M is the number of eigenvectors you're using, and so this is a free parameter to choose, right? So if assuming that we can do that and we can learn these things, how are we going to design a preconditioner around that information? Well, we do the following. So we take our top m eigenvectors of the covariance matrix of pi that we've extracted out using this procedure, and we basically rotate the state in such a way that those top m eigenvectors are aligned with the top m coordinate axes, right? The first m coordinate axes. So the idea is that we're constructing a transformation which will mean that then a diagonal preconditioner should work better, right? And then we apply a diagonal preconditioner, right, on that kind of rotated space, right? So the diagonal preconditioner itself can be just learned in the natural way by then estimating the marginal variances in the transform space. But we can also take its top m entries and just make them like using the eigenvalues that come out of this algorithm. So you have two different options here. There wasn't a clear winner in the experiments we did. Yeah, I've already said that. Good. So this preconditioner, the total cost of estimating and using it is going to be order dm squared. So as long as I choose the number of eigenvectors I'm learning to be like less than square root d, then I'm going to get my subquadratic cost. Okay, and this is something that we're still sort of developing, of course, and we're still exploring in examples. It is published in Max's thesis, but we're writing things up at the tail. But here's a kind of example and a logistic regression example of the kind of performance we're getting. So this is a logistic regression where there is some kind of low dimensional structure to learn, and you do need to be in that kind of setting in order for this thing to be, a sensible thing to do. But we compared to lots of different options, and on the y-axis is effective sample size per second. So this is kind of incorporating the computational cost. And you can see that as the dimension increases, this kind of turquoise and blue boxes, which correspond to two different versions of our algorithm, are doing the best, right? Whereas the dense preconditioning strategy, which is this kind of red one here, starts out doing very well, but eventually gets quite costly. So if I plotted the raw ESSs, the dense one would be the best. But when we incorporate the cost, our method seems to win out, right? So the PBAM here is this variational inference pre-training algorithm, patch, batch, and match. And again, in the setting that we tried it was also proving quite costly to do that pre-training compared to our approach. Okay. Okay, good. So that's it really from me. We've got lots of different things we can think of in terms of the theory. I think moving beyond the well-conditioned class, and there's natural kind of relaxations to do that, which I think would change the results here. Would allow us to say a bit more. Are things that we've thought about. Certainly thinking about nonlinear preconditioning is something we started doing, but we decided to publish what we had, and Max has got lots of nice thoughts on that. In the methodological work, you can think about how to choose the number of eigenvectors, and there are some heuristics in the literature for doing that we may explore. And also, we've focused on preconditioning here, but I think these results are a nice precursor to studying adaptive MCMC, and that's definitely something that Sam and I have discussed many times, for example, and that we're sort of interested in thinking about in future. But thank you very much for listening, and happy to take questions.